The most powerful way of reducing dimensions in multivariate data is to use something called principal component analysis, or PCA. And what it does is it tries to look for a bunch of correlated variables. Maybe you find that all of the amino acids are trending in the same direction, or all the biogenic amines are trending in another direction. So instead of having 20 amino acids and 30 biogenic amines, it's one amino acid group and one biogenic amine group. And so we've converted 50 dimensions or variables to just 2 dimensions, amino acids and biogenic amines. So by taking correlated variables and getting them 50 correlated variables into 2 uncorrelated variables, these are called principal components. So you can reduce tens, hundreds, or thousands of variables to basically 2 or 3 key features. And that's shown on the left here, where we're showing a plot of metabolomics data for several hundred patients. And we have green patients, red patients, and blue patients. And you can see that they are clustering. And we've converted the thousands of metabolites that were measured for each of these patients into these pseudo variables, 3 different plots, or 3 X, Y, Z axes. And those are essentially variable metabolite features. Another way of thinking about principal component analysis, where we can take some spectrum. This is an NMR spectrum where there's hundreds of peaks, and we've converted those hundreds of peaks into just 2 components. So we've looked at blood samples from animals that were treated with 2 different drugs, PAP and ANIT, and then control. And quite obviously, you can see there's a difference from the spectrum. So that's something that our eyes can see. But statistically, how do you show that? And this is where we've converted all these peaks, hundreds of peaks, into basically peak components and plotted this out on a scores plot. There are about 25, 30 controls. They're in the red circle. The ANIT group, there's 4 of them. And the PAP group, there's 4 of them in green. And we can see that they form 3 very distinct clusters. Just as our eyes can tell you, even if you don't know much about NMR spectroscopy, that the spectra are very different between the control, the ANIT, and the PAP group. What PCA does is it captures what should be visually detectable, because anyone can look on the left side and see that the spectra are distinct. And it shows that they are statistically separable and that there are certain features that can distinguish between these 3 categories. As a rule, if you can't see the separations with your eyes, the application of PCA probably won't help. Our eyes and our brain are very good at distinguishing multiple groups. Another way of thinking about PCA is to think of something that has a 3-dimensional shape and how it can be projected onto 2-dimensional screens. So let's take an example of a donut or a bagel, and we suspend it in space and we shine a light on the bagel. One way, we can get the shadow forming of an O, which is the characteristic shape of a bagel. If we illuminate the bagel on the other side, we'll produce something that looks like a sausage. Now that sausage shape tells us a little bit about the depth or thickness of the bagel, but it's the O projection that actually tells us more about what it is. If we only had the O projection, we could probably guess it's a donut or a bagel. If we had the sausage projection, we might think that it's a sausage, where in fact it's a bagel. So the O projection actually captures most of the variation of the object, and so it has what we call the largest eigenvector, and it forms principal component 1. The sausage or wiener shape has less information, and it would form principal component 2. Together, principal component 1 and 2 are enough to sort of describe the bagel. They describe its overall shape and its thickness. Now, PCA isn't just simply shining light bulbs or flashlights onto objects. It requires math. It involves something called singular value decomposition and the calculation of eigenvalues from a data covariance matrix. The data covariance matrix is sort of measuring the correlations, if you want. It's essentially an orthogonal transformation. It converts things from multiple dimensions into a smaller number of coordinates. It does a coordinate system transformation, and it maps out the things with the greatest variance in progression from the highest to the lowest. So typically you have in a data matrix for PCA, there'll be a bunch of samples, 100 samples, and then 150 metabolites that are, say, measured. And from there, you calculate the eigenvectors and the loadings. The eigenvectors are in blue, the loadings are in P, and essentially the scores, which are measured in T, represent a combination of both the loadings, P, and the variables in X. And so, let's say it would be the concentrations or weighted concentrations of a bunch of different metabolites. The example I gave was that maybe T1 would be the amino acids, and T2 might be the biogenic amines, and T3 might be the organic acids, all because they, for whatever reason, are related. Now, I want to give an example because the math for PCA can be very complicated, but there is some intuition that you can get with PCA. This is an example that was given to us by a colleague in the UK. He'd been looking at data from airports. In the US, there are about 5,000 airports. And what they did was they got information on the latitude, longitude, and altitude of all 5,000 airports. Now, this would be the equivalent of having essentially 5,000 subjects or patients and measuring 3 different metabolites, maybe alanine, urea, and creatinine, for instance. So this is inherently multivariate data. It's multiple variables, 3 variables, for 5,000 subjects. So you can use PCA, or principal component analysis, to simplify this and to see if there's some interesting clustering or trends that emerge from it. So remember, PCA is a way of extracting clusters out of data. So Roy Goodacre took all this data, ran it through a fairly sophisticated PCA analysis tool, and this is what he got. If you know a little bit about geography, you can see that what you're seeing is a map of the United States. There's the continental United States in the upper right corner. There's Alaska in the upper left corner. And then the lower left corner is Hawaii. And so these are essentially what you're getting is a cluster or a clustering set. So this is, sophisticated PCA with singular value decomposition. All the calculations essentially generated a map of the US. And in essence, it performed a clustering where one component, principal component 1, is essentially the longitude, and principal component 2 is the latitude. And it turns out that the altitude had almost nothing informative to provide. This illustrates that principal component analysis is mathematically equivalent to k-means clustering. And people have actually proven it using sophisticated math and theory. So you can generally interpret PCA as a form of k-means clustering. And this is why we introduced clustering before we introduced PCA, just to show you that the two are very much related. So with PCA, you can take multivariate data and you can essentially obtain clusters of data that are mostly normally distributed with characteristic means and variances in PCA space. You can then use t-tests and ANOVA tests to determine if these clusters are significant, if they're different, or if they're basically the same. So here's an example where we've got 3 clusters showing up. To our eyes, we can see 3 clusters, and then we can use ANOVA tests to actually confirm that what our eyes are seeing and that these tests or these clusters are indeed statistically different. Now, PCAs will generate 2 different types of plots. The most commonly illustrated plot is the scores plot, and we've just seen that one where we show these three clusters, the red, the blue, and the green cluster. And it tries to plot out, in this case, these three different subjects or patients in metabolite dimension space. So there's three dimensions, x, y, and z axes. X-axis would correspond to one set of metabolites, the y-axis another set of metabolites, z-axis to another linear combination of metabolites. But the result is that the subjects that are being measured seem to cluster into three distinct groups. So that's a scores plot. We also have a loadings plot, and this illustrates how specific, in this case, metabolites differ or contribute to the different principal components. So there are, in some cases, these metabolites that are shown here, the ones on the far right, drive the separation on one side, and metabolites on the far left drive it on the other side. So the separation that we see in the scores plot are driven by the metabolites on the extreme right and the extreme left. Now, depending on the shape of the scores plots and where the clusters are, we can also determine or sometimes try and map the loadings plot to see which is driving the shape or the separation. As a rule, it's the metabolites that are at extreme corners, extreme edges that drive most of the separation. Now, PCA is a way or a technique for separating samples, subjects, patients according to their genes, proteins, or metabolites. Now, if those subjects are distinguishable by genes, proteins, or metabolites, you should see distinct clusters. If those subjects are not distinguishable, then sometimes it's just wise to give up. There's a tendency to always believe that every experiment will lead to success, and that's not often the case. PCA is a way of essentially assessing whether you are pursuing a useful line of inquiry or whether it's time to perhaps stop and think about another type of experiment. If you cannot separate your 2 or 3 classes based on a PCA plot, and that separation is non-obvious, then applying more and more statistical techniques can actually get you into more and more trouble. However, there are some tricks that can help tease out separations that are not quite as obvious to the eye as would be expected.